Hello, DDECS 2022. My name is Owen Hoffend. I'm a student from the University of Michigan in the USA, where I study under my advisor, John Hayes. Today, I'll be presenting on the topic of analyzing correlation in multilayer stochastic circuits. I regret being unable to attend the conference in person, but I'm grateful to the DDECS staff for their hard work in accommodating a virtual format. As I am recovering from COVID-19 and still have a bit of a cough, I'll be using a pre-recorded presentation today, but I will be here live to answer questions afterward. I hope you enjoy my presentation. For this talk, I'll begin by outlining the basics of what stochastic computing is and how it differs from conventional binary-based computing. This research is focused particularly on understanding the impact of correlation in stochastic computing, so the following section will discuss the benefits and drawbacks of correlation. Following this, I'll introduce the multi-layer correlation analysis technique that we've developed. Lastly, I'll give a case study showing how this analysis technique can be applied to solve practical stochastic circuit design problems. Stochastic computing is an alternative approach to digital computation that encodes data within random sequences of ones and zeros instead of using binary. A stochastic number x is a sequence of n zeros or ones with a value represented by px, the probability that any bit of x is 1. Therefore, a basic unipolar stochastic number represents fractional numbers in the range of 0 to 1. Given a bit stream, px can be approximated by counting the number of ones and dividing by the bit stream length n. The precision of a stochastic number is tied to the bit stream length. For instance, here we see 3 examples of stochastic bit streams, each of which approximates the true value of 1/3. The longer bit streams achieve values much closer to 0.33 repeating than the shorter ones do. Circuits operating using stochastic numbers instead of binary tend to achieve better area and fault tolerance at the cost of lower precision and higher latency. For instance, here we see an AND gate, which multiplies the input probability values when the input bit streams are statistically independent. Compared with an adder-based binary multiplication circuit, the stochastic AND gate multiplier has substantially lower area. Another fundamental operation we can do is stochastic scaled addition, which is similar to conventional addition, except that the result is scaled to maintain in the range of 0 to 1. A single mux gate achieves scaled addition when the select bit is independent from x and y. There are many exciting applications that are currently being explored by the stochastic computing research community. Here we've highlighted 2 that are particularly relevant to our current research. The first is an example of a near-sensor stochastic edge detection circuit constructed using no more than 3 logic gates. It is able to produce convincing edges after only a handful of clock cycles, making it extremely power and area efficient, ideal for battery-constrained image processing environments such as mobile cameras or drones. Stochastic computing has also been extensively studied as a paradigm for machine learning hardware. A basic stochastic neural network consists of a set of AND gate multipliers followed by a mux adder and a tanh activation function. The stochastic tanh function is notable because it requires only a small finite state machine, which is far simpler than conventional approaches. Now we will discuss correlation and how it relates to stochastic computing. In stochastic computing, bitwise correlation between a pair of bit streams is defined by the likelihood of encountering overlapping ones relative to the values of the 2 bit streams. For example, here we see 3 cases in which a pair of bit streams x and y with probability values 0.75 and 0.5 are either fully correlated, uncorrelated, or anti-correlated. The overlapping ones are highlighted, and the corresponding overlap probability is shown. In stochastic computing research, correlation is typically measured using the stochastic cross-correlation, or SCC. With this measure, SCC equals 0 is assigned to the uncorrelated case, and SCC equals plus or minus 1 is assigned to the fully correlated and anti-correlated cases, respectively. The SCC equation is shown. It relates correlation to the bitstream values and overlap probability. Early stochastic circuit designs assumed that the input bit streams were all uncorrelated with each other, corresponding to SCC equals 0. However, more recently, it has been shown that stochastic circuits approximate different and potentially useful functions when their inputs have correlation values other than 0. For instance, the AND gate that typically computes multiplication now computes the minimum function when the inputs have maximum correlation, as shown in the example on this slide. Similarly, an XOR gate with correlated inputs computes an absolute value subtraction operation. These operations expand the breadth of functions that may be implemented more efficiently with stochastic circuits than with conventional binary. For example, the edge detection circuit that we saw before exploits fully correlated data inputs in order to compute 2 absolute valued subtract operations, which are then summed using a mux-scaled adder. The circuit therefore computes the equation shown for the output probability. This function is known as Roberts cross edge detection. The result is one of the smallest known edge detection circuits by area. We just saw how correlation can be exploited to enable a wider variety of stochastic functions. However, now we'll highlight an important problem in stochastic circuit design that is also tied to correlation. Consider a pair of parallel XOR gates where all inputs are fully correlated with SCC equals 1 with respect to each other. Using the methods we'll discuss later, it's possible to show that the average output SCC after the XORs is about 0.3. Now suppose that the output of these XOR gates is fed into an AND gate. Previously, we showed that an AND gate computes multiplication when its inputs are uncorrelated with SCC equals 0, and the minimum function when they're fully correlated with SCC equals 1. The question is, what function does this two-layer circuit compute? Does it compute the product of the two absolute value subtracts, or the minimum? As it turns out, the answer is neither. When SCC equals 0.3, the AND gate produces the weighted sum of the multiplication and minimum functions, where the weight is based on the input correlation. In practice, such partial correlation is rarely desirable, and usually leads to correlation error, which is the difference between the circuit behavior under the ideal correlation and the actual circuit behavior. Correlation degradation and its resulting correlation error poses a major design problem for designers of large multi-layer stochastic circuits because it complicates hierarchical design abstraction. In conventional binary circuit design, a given subcircuit can generally be expected to perform the same function regardless of what subcircuits came before it, which is a critical assumption enabling abstraction. However, we've shown that the assumption does not hold in the case of stochastic circuits. Therefore, it is necessary to develop a sound theoretical understanding of correlation degradation and correlation error for multi-layer circuits. This topic has been explored in prior research, resulting in mostly ad hoc methods. The problem becomes increasingly difficult when the circuits have more than two inputs and outputs, and/or more than one layer of logic. For instance, this example shows a two-layer circuit with 4 inputs, 4 intermediate signals, and 1 output. Generally, the stochastic function implemented by layer 2 depends on the correlations between all 6 pairs of intermediate signals, which in turn depend on the layer 1 circuit and its input correlations. Next, we'll discuss a new technique for performing correlation analysis for these complex multi-layer circuits. At a high level, the analysis we will perform will take a vector of input probabilities and some information about the input correlation and combine them into a joint input distribution. Then we will apply a mathematical model of the circuit to obtain the joint output distribution. From this, we will extract the output probability vector and correlation information, which will be used to determine how a given circuit layer's output correlation will affect subsequent layers, and how much correlation error there will be. We'll begin by solving the problem of succinctly representing the numerous pairs of correlations. To do this, we'll adopt the use of correlation matrices from statistics, such that the ijth entry of the matrix holds the correlation between the ith bit stream and the jth one. In general, correlation matrices are always symmetric, with ones down the main diagonal. As an example, the edge detection circuit from before requires that all pairs of data inputs have SCC equals 1, and the select input S must be uncorrelated with all other inputs. On the other hand, the required correlation matrix of a 3-input AND gate multiplier is the identity matrix because all data inputs must be uncorrelated, having SCC equals 0 with respect to each other. With correlation matrices, we say that any group of bit streams that all have the same SCC value with respect to each other are mutually correlated. For instance, we can say that the board data inputs to the Roberts cross edge detection circuit are required to be mutually correlated with SCC equals 1. This is shown in the group of ones highlighted red on the right. This matrix is an example of a more general class of block diagonal correlation matrices, in which subsets of the bit streams are correlated, but these subsets are independent from all others. The general form of block diagonal correlation matrices is shown on the right. Lastly, if a set of bit streams have the identity correlation matrix, then they are mutually correlated with SCC equals 0, which is to say they are all uncorrelated. Now we'll use correlation matrices to help define the joint input distribution for a given circuit. We can express this joint distribution as the so-called probability transfer vector, or PTV. Each entry of the PTV corresponds to the probability of seeing a given bit pattern on the circuit inputs. So, for a circuit with 3 inputs, the PTV is a vector of size 8 containing the probabilities that the inputs are 0, 0, 0 through 1, 1, 1. Then, given a correlation matrix, Our goal is to write the PTV as a vector-valued function of the input probabilities. We notate this as V sub c of P of x in bold. Here we see three basic examples of what PTVs look like for a circuit with two inputs when they are uncorrelated, fully correlated, and anti-correlated. In this example, the inputs both have the value of 0.5. Note that the bottom entries, highlighted red here, give the probability that both inputs are 1 simultaneously, indicating an overlap, and that, as expected, this is highest for the fully correlated inputs and lowest for the anti-correlated inputs. The PTVs that we just saw were for circuits with only two inputs. A key result of this research are these three equations, which specify how to construct the PTVs for any number of mutually uncorrelated, fully correlated, or anti-correlated inputs, respectively. In the interest of time, we will not go further into detail about how these equations are derived. Please see our paper for details. For now, just know that they exist and they are very useful for circuit analysis, as these so-called fundamental cases are by far the most common. Additionally, next we'll show how to form PTVs for more complex correlation matrices by combining these fundamental PTVs. There are two identities that we've found that can greatly expand the types of correlation matrices that we can generate PTVs for. The first is the linearity property, which states that if all entries in two correlation matrices have the same sign, then the PTV for the scaled linear combination of these two matrices is equal to the linear combination of the PTVs for each individual correlation matrix. The second involves block diagonal correlation matrices. Since each submatrix is independent from all others, the PTV for a block diagonal correlation matrix can be shown to be the tensor product of the PTVs for each individual submatrix. Now we'll see an example of both PTV generation identities being used to form a PTV for a relatively complex correlation matrix. First, observe how the matrix in the upper left can be written as a linear combination of matrices containing only ones and zeros. The left one is a block diagonal correlation matrix, while the right one represents mutual correlation with SEC equals 1. This allows us to write the final PTV by performing the tensor product on two smaller 2x2 fully correlated PTVs, and computing its linear combination with a full 4x4 fully correlated PTV. Now that we know how to write the joint input distribution, we need to know how to apply a circuit's function to it in order to yield the corresponding output distribution. Fortunately, this is extremely easy to do with an existing body of research known as probability transfer matrix, or PTM theory. A PTM is a matrix whose rows represent possible input patterns, just like PTVs, and whose columns represent the resulting output probabilities. They are essentially a generalization of the Boolean truth table. For example, the PTM for an AND gate is shown here. We can obtain the output PTV just by computing the matrix vector product of the PTM and the input PTV. Finally, now that we've found the output PTV, we'd like to extract the output probabilities and correlation back out of it, and essentially do the reverse of the PTV generation process which we showed previously. For the output probabilities, we found a neat equation that multiplies the output PTV by matrix B, which we call the binary integer matrix, or BIM. Each row of the BIM simply contains as its columns the binary encoding of the row index. In the example, we see the equation applied to the PTV for two bit streams to find the output probabilities. Note how multiplying by the BIM has the effect of computing the marginal probabilities, which is exactly our goal here. Lastly, we'll show how to compute the output correlations. Recall that each entry of the output correlation matrix is the SEC between one pair of output bit streams. Also recall that the SEC equation depends on the bitstream probabilities and the probability of an overlap occurring. We just found the vector of output probabilities, so we know these bitstream probabilities. The only thing we need to find now is the overlap probability. Using binary integer matrices again, we found an equation that computes the overlap probability of a given pair of output bit streams from the output PTV. Intuitively, the equation works by computing a weighted sum of all possible ways for an overlap to occur on a given pair of output bit streams. Now we'll discuss a case study showing how this new correlation matrix analysis technique can be applied in a practical multi-layer stochastic circuit design setting. For this case study, we will evaluate the correlation properties of the stochastic scaled adder, which computes the function 1/2 of x1 plus x2. This function is ubiquitous throughout stochastic circuit design, especially within neural networks and digital filtering circuits. The adder is typically implemented using a mux gate. It turns out, however, that it's possible to find alternative circuit implementations that yield the same expected output probability. One such example is the so-called majority gate, shown in the upper right, which outputs a 1 if 2 or more inputs are 1, or 0 otherwise. We can therefore say that the mux and majority gates are stochastically equivalent. Prior work has shown that it's possible to reduce circuit area by intelligently substituting equivalent subcircuits. Here, we will evaluate whether the same can be done to reduce correlation error. In the bottom right here, we see that the PTMs for the mux and majority gates are different, despite them both implementing the same function. This gives us a clue that the two adder circuits do indeed affect correlation differently. The first multi-layer circuit that we will test for our experiment is a 3-layer image processing circuit consisting of 4 instances of the Roberts-Cross edge detector followed by a max pooling layer. We'll model the input correlation to this circuit using the block diagonal correlation matrix shown, denoted CRC. Using CRC, we'll apply our correlation analysis technique to find the resulting expected correlation matrix entering the layer 3 max pooling circuit. For this tree of OR gates to compute the maximum function, all of the bit streams arriving from layer 2 must be mutually correlated with SEC equals 1, otherwise there will be correlation error. We will calculate this correlation error, then the mux gates will be replaced with majority gates, and the experiment will be rerun to see if the correlation performance improves. The second multi-layer circuit we will test is a small neural network layer design. The first 2 circuit layers perform the dot product between the data inputs and a set of positive weights, resulting in Z positive, and a set of negative weights, resulting in Z negative. The final layer subtracts Z positive and Z negative, then applies a rectified linear or ReLU activation function, which is a common neural network activation function in machine learning. By again designing layer 3 to expect inputs correlated with SEC equals 1, the AND gate with one inverted input computes exactly the ReLU of Z positive minus Z negative, allowing us to exploit this correlation property to reduce the area. Circuit 2 is also slightly more complex than Circuit 1 in that the input correlation matrix should be block diagonal. To maintain as much correlation between Z positive and Z negative as possible, the group of data inputs should be correlated with each other, and the group of weight inputs should be correlated with each other. However, the data inputs should be uncorrelated with the weights in order to allow layer 1 AND gates to perform multiplication. Additionally, the select input for the mux adders should be uncorrelated with all other inputs. The required correlation matrix is shown. For this circuit, we'll perform the same experiment as Circuit 1. We'll find the correlation matrix entering layer 3 and the corresponding correlation error before and after mux adders are replaced with majority adders. To evaluate the change in performance of the 2 multi-layer circuits when the mux adders are replaced with majority adders, we ran an experiment in which both circuits were given 100,000 test inputs. For the image processing circuit, these test inputs were 3x3 pixel patches, randomly sampled from the popular MNIST, handwritten digit, and CFAR10 object datasets. For the fully connected neural network circuit, we used uniform random inputs. For each test input, we computed the PTV according to each circuit's required input correlation, and subsequently the output PTV via matrix multiplication with the PTN. From here, we used the theorems discussed previously to find the expected output values and correlation matrices, respectively, at each layer. It's critical to note that these correlation results are computed in an exact fashion using matrix-based math, instead of relying on the bit-level simulation, which would require thousands of samples for each test to obtain accurate results. This chart summarizes the change in output correlation at layer 3 of both the neural network circuit, which we saw in the previous example, as well as the Roberts-Cross edge detection circuit from before. The results for the Roberts-Cross circuit are separated by the input dataset. On the left is MNIST, and in the center is CFAR10. We observe that the average layer 3 correlation increases for both circuits when the mux adders are replaced with majority adders. We also note that the percentage of correlation increase is highly dataset dependent, as the switch to majority gates increases the average correlation by 47% in the case of CFAR10, but only 2.4% in the case of MNIST. We note that this is likely because the pixel values in MNIST tend to be more correlated with each other than CFAR10, which results in better bit correlation after the first layer. Finally, we show the change in output correlation error, measured as the average absolute difference between the ideal function and the actual output computed using our method. Recall that, for both circuits, layer 3 expects positive input correlation, and that we previously showed that switching from mux to majority gates resulted in an increase of correlation at this layer. Here, we see that the output correlation error is lower for all cases when majority gates adders are substituted. In particular, the decrease in error is most substantial for the neural network circuit, which shows an 83% drop in correlation error. These results for this case study show how our matrix-based correlation analysis technique allows designers to evaluate different circuit designs to maximize correlation performance. In conclusion, our research is the first to apply correlation matrices to stochastic computing in order to analyze correlation in circuits with more than 2 bit streams at the input and/or output. We've also shown how to convert correlation matrices into PTVs so that existing PTM-based approaches can be used to model circuits with a specified input correlation matrix. We then showed how to extract correlation and probability information from output PTVs in order to determine circuit behavior without bit-level simulation. Finally, in our case study, we demonstrated that stochastically equivalent subcircuits can be substituted to reduce correlation error, as was the case for substituting mux adders with majority adders in the image processing and neural network circuits. That is the end of my presentation. Thank you for listening. Are there any questions?